Hello, we are Group 21 and we will be presenting additive manufacturing for biomedical applications. My name is Matthew Wong.
I'm M. Sazid Hassan.
I'm Daniel Williams.
And I'm Victoria Whitten.
The development of biomedical applications has progressed drastically within the past century due to the dedication of scientists and engineers. Evolution of this field will never end as there will always be potential for improvements. From the features of prosthetics and implants to ease of manufacturing to reduction of costs. With continuous advancements in the technology, universities and medical centers combined have been effectively researching methods of advancing these improvements. One of the most effective ways discovered of decreasing costs and easing the fabrication process is through additive manufacturing. This procedure uses computer programming such that a machine completes the construction electronically without any supervision necessary. Some amazing examples of additive manufacturing plausible in the future consist of bones, skin, organs, and even entire functioning limbs equipped with sensory abilities.
Additive manufacturing can be used to form complex cellular structures and mesh arrays. This can thus be used to form patient-specific biomedical implants. Additive manufacturing includes the fabrication of hard tissues, bones, especially knees and hip stems. One of the recent successful procedures that are being practiced to fabricate these implant structures is electron beam melting, also known as the EBM. This uses a 3D CAD model of the implant structures and focused electron beams to create the design patterns on a desirable metal powder layer. The successive layers are raked over each other until the final structure is formed. One of the advantages the EBM comprises of is the flexible use of various density metals to fabricate required cellular mesh and foams. Titanium is preferred over other metals due to its high specific strength, low density, corrosive, and fatigue resistance. However, titanium alloys exhibit adverse stress to the implant surface that can cause malfunction of effective bone tissue growth and biomechanical compatibility.
Additive manufacturing of hip implants, traditional versus 3D printed. Traditionally made hip implants are becoming a thing of the past due to their rigidness and tendency to cause infection or weakening of the bone, which makes them ultimately fail. 3D printed hip implants take much less time and money to manufacture due to there being only one step process and needing only one person to operate multiple machines. Traditional hip implants require forging, machining, as well as special finishing for optimal use, which requires a lot of equipment, time, and money. However, 3D printing creates a better finish that allows the hip implant to bind with the bone more effectively, causing less problems for the patient in the future. As you can see here, the 3D printed hip implant has much more detail in its surface finish, which is a key component that helps the implant bind with the bone, whereas the traditional hip implant is very smooth, making it harder for the bone to integrate with it, and it tends to require much more corrective surgery in the future. This technology, once fully explored, has so many bone applications. In theory, it could potentially rebuild a viable human skeleton with only a small amount of bone for it to integrate with. In the future, further technology improvements will be incorporated with 3D printed implants, such as microchips inserted inside of them. These microchips would monitor stresses on the implant, temperature of the metal, and integrity of the replacement once it is inserted into the patient. In doing so, doctors can see when the problem is within the implant without having to do surgery, as well as engineers can better design future implants based on stresses and record on, which in turn opens up an opportunity to make custom implants for individual needs. For example, a very physically active person would require a stronger implant that can absorb more impact than that of an elderly person. Such characteristics can be manufactured through 3D printing quickly and accurately for each individual patient. As shown in the photo, by using additive manufacturing, a much better surface finish can be achieved. This surface finish does two things. It provides better shock absorbance than that of a traditional hip replacement. As well, it allows the bone to bind much more effectively. By using additive manufacturing, the implant success rates have gone up, less corrective surgery is required, and less stress is put on the patient, which all in turn help improve their quality of life.
Another biomedical application is 3D organs made from stem cells, which will be used for transplants. This will reduce the risk of patients rejecting the new organ because it uses the patient's own stem cells. Organ rejection happens because the cells in another person's organs are foreign to the patient, which result in a massive immune reaction against these new cells. The long-term goal for organs to be produced are heart, lungs, liver, and kidney. Patients waiting on these organs often have very long wait times, and many die before receiving them. There is hope these parts can be created due to the evidence of a trachea, bladder, and urethra being printed. The beginning stages of bioprinting started with simple structures which survived outside of the body, such as skin and cartilage. From here, more complex structures could be developed. One major issue within this project is matching the complexity of the real-life body parts with the artificial ones made from stem cells. The heart will most likely be a starting point for the vital organs. Although it is still a complex system, it is the most understood and therefore one of the easiest to begin with. Organs such as the kidney and liver are more complex due to their complicated biochemistry needed to function. To fabricate the material, live stem cells are taken from a biopsy and are then multiplied to form a bioink. The bioink is then injected around a temporary mold made of hydrogel. Once this is completed, the stem cells grow and mature, then the hydrogel can be removed, leaving the final product. This process is shown through the image. To produce a functional organ, another material is needed. This material is called fugitive ink. This material is made so that it melts when it's cooled, which can be suctioned, resulting in tunnels that act as blood vessels and allow the blood and nutrients to flow. Bioprinting is very similar to 3D printing while having the potential to create living tissue. This follows the 3D printing process, but sometimes requires being executed around a scaffold structure of the organ made out of biodegradable material. This can be done by decellularization of a whole organ and recreate it using the patient's cells. If a biodegradable scaffold was made, once the new cells are fabricated over the scaffold can be broken down, leaving the functioning organ, which can then be transplanted. This method is successful on a lower scale and is being worked on to be possible on a fully functional organ. It's predicted that in 5 years, skin will be ready to be implanted, and 10 years from now, partial or full cartilage implants will be possible. And it is also predicted that organ transplants will be possible within our lifetime.
Recently, bioengineers have successfully created prosthetic limbs in which users can not only control with their mind, but interpret the sense of touch as well. This is executed through implanting minuscule sensors in the motor cortex of the brain. Nathan Copeland, a man who was mostly paralyzed from the chest down in his teens, was given the opportunity to be the first person experiencing sensation from a prosthetic limb. To the success of the University of Pittsburgh, Copeland is 84.3% accurate in identifying which prosthetic finger is touched while blindfolded. This advancement will be a stretch for additive manufacturing within the next 10 years due to such complex components combined with so many movable parts. Moreover, the prosthetic needs to be manufactured with wires integrated throughout the entire structure. Achieving this feat will be a groundbreaking advancement attainable with the aid of additive manufacturing within the near future. Evidently, through these astonishing advancements actively commencing in the additive manufacturing of biomedical applications, there is an extremely promising future for medicine. The progression of these applications has proven quite remarkable, as in past, amputations could be fatal by disease. But soon, prosthetics will actually become an improvement on natural limbs. From all the advancements depicted throughout this report, it is clear that additive manufacturing is continuously improving and becoming a part of all medical technology. Furthermore, machinery is far more precise with its accuracy of construction, assembly, and consistency of producing tailored parts. Consequently, it is indisputable why we are evolving towards the assistance of additive manufacturing. To summarize, most of these elaborate creations were unthinkable only a few decades ago, and at this rate, the innovative technology to come will be unbelievable. This concludes our presentation.